So in the last lecture, we understood what are the basics that are required to solve this question, that is N-channel MOSFET. Now if you observe the question, here what they have given, VDS is less than VGS minus VT, okay, and the second thing what they given is ID equal to VGS minus 1 into VDS minus VDS square by 2 milliampere. If you compare this equation with the standard equation, see what is the condition? When VDS is less than VGS minus VT, then that region of operation. What is the region of operation? In the last class we saw when the value of VDS is less than VGS minus VT, then the region of operation is linear region. What is the corresponding formula for drain current? It can be written as mu n C ox omega by L into VGS minus VT into VDS minus VDS square by 2. Now take this is standard equation. If you compare this standard equation with the given data, so in this given data, what's happening is that mu n C ox omega L is not there. It means they kept the value of mu n C ox omega by L equal to 1. First conclusion. Next, if you observe inside the formula, VGS minus VT is there. In place of VT, if the given question, if you observe the question, we are having 1. So from this second data is threshold voltage equal to 1. We understood this second one. So these things we can covered when our MOSFET is in linear region. They are telling that if it is in linear region, then we can consider this data. Suppose if it is entering into, see, this is what is this? When VDS is greater than or equal to VGS minus VT. When VGS will become greater than or equal to VGS minus VT, then the region of operation will become saturation. So the conclusion is, in the second case, our MOSFET will be entering into saturation region. When it enters into saturation region, once again we know the formula that the value of ID can be written as mu n C ox omega by 2L into VGS minus VT whole square. Of course, in our question, channel length modulation effect is not being considered. So you can neglect this value. So we are going to consider only remaining portion, but already what we understood, if you observe this question one more time, they haven't considered any value before the value of VGS minus whole square. So once again what they are treating mu n Cx omega by 2L, that whole value they are considering it as 1. And if you observe inside, actually we are here also we are having VGS minus VT whole square. In place of VT we are having 1. So it is again one more time it's conclude that the value of threshold voltage equal to 1. Okay sir, now how to solve this question? See, the question is what is the value of IDC? If you carefully observe this point, just apply KCL. If I will apply KCL here, what will be getting? According to KCL, if I will apply KCL at this junction, according to Kirchoff Current Law, algebraic sum of incoming current, I am just calling, let us take one thing. This is I am calling it as IX. This current I am calling it as IY, and here IDC is already there. According to Kirchoff Current Law, IX equal to IY plus IDC. What are all the parameters that we know here? We know the value of Ix, that is given as 2 milliampere. Already we know that. But the value of IY is not known and the value of IDC is not known. Of course, we have to find out the value of IDC only. So from here, what is the conclusion is, if you figure out the value of current consumed by the transistor 1, then you can easily identify the value of IDC. So it is time to explore the value of IY. IY means that is current consumed by the transistor 1. Okay sir. Now that is current consumed by the transistor 1 means drain to source current consumed by the transistor 1 ID. We have to identify the value of ID1. I am calling it as ID1 because that is transistor 1 drain to source current. That is simply called IY here. So I am calling it as IY equal to, that is known as drain to source current of the first transistor. Okay sir, how can I figure out the value of drain to source current of the transistor 1? In order to know that, you have to know the region of operation because they have given two expressions for drain to source current. So without knowing the region of operation, if you are in linear region, then you have to go with the first expression. Suppose if your transistor is being operated in the saturation region, then you have to go up with the second equation. So in order to know that, once again we have to check all these conditions. What we need to do, suppose if in order to know this linear or saturation region, we have to check all these values. We have to identify the value of VGS, then we have to calculate the value of VDS less than VGS minus VT. Everything we have to do. Shall we start now? Yes. So it's time to explore that expression. Let us see. The first thing is from the given diagram. See, what is the value of, if you observe here, this terminal will be simply treated as drain terminal VDD. Yes, sir. What is the voltage that they have given? The given voltage is 5 voltage. If at this node we are having 5 voltage, then what is the available voltage at this node? We are also here also we are having same 5 voltage. Yes, sir. Now keep your attention only with this transistor. I am drawing it separately for your understanding. It is given like this. Yes, sir. So gate terminal is connected with the ground. I can call it, the value of gate voltage is 0. Next, if you observe, this is source terminal. How can I name this? With respect to the direction of the current. Because current direction will be given only at the source terminal and current is going out. It means N channel MOSFET. Now at this terminal they have given that is 5 voltage. So this voltage will be simply treated as drain voltage. Of course, source voltage also given here. The value of source voltage what they have given is minus 2 voltage. And we also know the value of VT, threshold voltage, already we found from the data, that is 1 voltage. Can we check now? Yes. What are the things that we have to figure out here? VDS, first drain to source voltage. This can be written as VD minus VS. What is the value of VD? Value of VD is 5 minus, what is the value of VS? That is minus 2. So this voltage is going to be 7 volt. So we calculated the value of VDS. Next, let us explore the value of VGS. VGS means this can be written as VG minus VS. What is the value of VG? Gate voltage. Gate voltage is 5 minus, what is the value of VS? VS is already given as minus 2 voltage. So the sorry guys, here I made a mistake. 1 minute. See, my mind was going with the VD once again. Forgive me. Change the data. What is the data we have to change? VG. What is the value of VG? 0 minus VS value is minus 2. This will be equal to only 2 voltage. Okay, sir. After finding the value of VDS and VGS, what we have to do? Next thing is we have to check these conditions. In order to know the region of operation, first thing is you have to cross check whether VGS is greater than VT or not. Where is VGS? VGS equal to 2 voltage, sir. If the value of VGS is greater than VT, then only transistor will be entering into linear or saturation region. Because we know the condition, if the value of VGS is less than or equal to VT, then it will be in cutoff region. It will not turn on. Directly you can write the value of ID equal to 0 ampere. So here condition is satisfied that the value of VGS is 2 voltage. It is greater than the value of threshold voltage 1. Next, we have to check. We have to identify the value of VGS minus VT in order to know the region of operation. Let us go through that. VGS minus VT is how much? The value of VGS is 2 voltage minus VT is 1 voltage. Of course, it is 1 voltage, sir. Finally, we know value of VDS is 7. Already we have been explored that. See, VDS is 7. It clearly indicates that the value of VDS is greater than the value of VGS minus VT. So what is the conclusion? Whenever the value of VDS is greater than or equal to the value of VGS minus VT, if the value of VDS is greater than or equal, any one condition is satisfied, then automatically we can conclude that the region of operation is saturation region. So once your transistor is entered into saturation region, then what we can conclude from here? Okay, sir, transistor is being operated in the saturation region. If it is in saturation region, then its correspondent expression for the current is given. Yes, sir. In the question they have given the value of ID equal to VGS minus 1 whole square milliampere. That is the drain to source current flow. For both the transistor, it is common expression for both the transistor we can take. So let us take that. Whenever transistor is being operated in the saturation region, then the drain current can be written as VGS minus 1 whole square milliampere. What is the value of gate to source voltage? We know that the value of gate to source voltage is 2, I think, right? Yeah. Gate to source voltage is 2. Let us substitute 2 minus 1 whole square milliampere. 2 minus 1 is 1. 1 square will be 1 only. So 1 milliampere. So we successfully calculated the current consumed by the first MOSFET. Now according to KCL, we know, see, from here I can easily say the current IDC will be equal to 2 milliampere minus current consumed by the first transistor, yes or no, that is drain current, that is 1 milliampere. Just now we have explored, so the resultant answer is 1 milliampere. So what is the current expression? So the correct expression or the correct value for the given question is 1 milliampere. So from this question we have been observed so many things. What are the things? First, we understood that how to check the region of operation. So in order to check the region of operation, we have to explore the value of VDS, then we have to explore the value of VGS. Then first step, check whether the value of VGS is greater than VT or not, and then find the value of VGS minus VT, then cross check whether VGS minus VT is greater than VDS or less than VDS. According to that conclusion, you can define region of operation. Once you define the region of operation, then you can take the expression for current. Maybe while observing the first question, it seems to be, sir, it is too difficult. No, while solving more and more questions, we are in the beginning. After solving 2 to 3 questions, it will become very easy. Okay, so this is all for this lecture. Remaining things we will see in the next class. Thank you all.